To the second week of this program. So today, in the first talk we have Professor Yannick Sire from Johns Hopkins University. So Yannick,
okay, so well, thank you for still attending this second week, and what I would like to talk today, it's two things. First, I would like to give a sketch, or at least give the general idea on how to prove regularity of harmonic mappings in higher dimension. Last time I proved I sketch, or even with some details, the case of surfaces. Now I would like to see in 3 dimension and higher for the dimension of the domain. And so it's going to be closing basically the part of classical harmonic maps, I should say. And then I will move to the free boundary case. And today I will explain the problem of harmonic mappings with free boundary and the link with some non-local equations. And then in the last 2 lectures, on I think Thursday and Friday, I will explain, I will develop on the flows for the free boundary case. But today I would, last time I explained how to prove full regularity for harmonic maps from surfaces into weak harmonic maps from surfaces into spheres or any Riemann manifold. What I would like to explain now is how to kind of overcome the counterexample of Rivière of a weak harmonic map from the 3-ball into the 2-sphere, which is discontinuous everywhere. So as I mentioned, this counterexample tells us in general we cannot hope for regularity in 3 dimensions and higher. However, what Rivière proved is that he considered only a weak harmonic map. Okay, so a weak solution of the equation. What about if you ask more? If you ask, for example, your solution coming from minimizing energy. So then, in this case, what one can prove is that you indeed have regularity or partial regularity. And this is what I would like to explain today. Are there any questions or on that? So really I want to depart from surfaces and investigate what can we hope what can we hope on in the higher dimensional case. So what I would like to prove somehow, at least sorry, there is a problem with my pen. Sorry. So what I would like to explain is the following theorem due to Shane and Uhlenbeck in the 80s. So let's take the dimension bigger than 3, and let's take a map which is an H1 map from a closed manifold into another closed manifold. So the dimension of M is n and is bigger than 3. And let's assume that the map U is minimizing. So I will not state exactly what this means, but I kind of explained it already. I have an energy, and so a minimizer is just like a minimizer in a reasonable sense of the energy. And so it's pretty natural things to consider. So what I would like to prove is that such map are always infinity from away from a closed set sigma. Okay, so sigma is closed, and this is the biggest closed set. It's such that it's a place where the map is singular. Okay, so it's a place, I would say, a little bit more where the map U is discontinuous. And so we know what this singular set is, like if the dimension is 3, sigma is discrete, it's finitely many points. And when n is bigger than 4, like the Hausdorff dimension of sigma is n minus 2. So n minus 3, sorry, n minus 3. So it's like this means that the set is codimension 3 for minimizing maps. So in dimension 4, the singular set in general is one-dimensional in the sense of Hausdorff measure. So of course, this is a very general case. If you assume more, like on the domain or the target, you might hope to have a singular set which is smaller. But in here, this is a general statement, okay, for map. Is there any? So you see that in dimension 2, this statement is absolutely not contradictory with the statement of being completely smooth. Dimension 2 is not included in this statement. Okay. All right. So I will not. So the proof is quite lengthy and like a bit technical. Even if now there are like many different proofs which are like doable. But what I would like first what I would like to do is that like sketch like the general idea of how to prove this type of statement. Okay, so I will not give a proof, but somehow I give you the main steps. So this type of statement is also first to remember it's a reminder of the last lecture is that but the only thing which is needed is to prove continuity. If U is continuous, then it's infinity by standard bootstrap. So we have to concentrate on the zero order theory of regularity. And so the first lemma, which is extremely important and has a lot of consequences, is a monotonicity formula. So what you can prove is that under exactly the same assumptions. So now, since I'm interested in regularity, let me assume that the omega, so the domain of the map, it's a local result. So let me assume the domain of the map is the ball, the unit ball, for instance, like with the flat metric. Okay, like for the regularity purposes, it doesn't change anything to consider this case because it's a local result, which is a minimizing map. Then the following is true. So for any x in omega and any little r like smaller smaller than okay, let me put the quantifiers. It's going to be more clear. And let me write it slightly differently. So the statement of the monotonicity is that for all x in omega, and all are positive, and less than distance away from the boundary, okay, then the quantity 1 over r to n minus 2 integral over b little r of x of gradient u square dx is non-decreasing in r. Okay, so this is a very important tool. Okay, this statement tells you that this rescaled energy is monotone in the radius. Okay, so this lemma, which is one of the first things you try to prove in this kind of case, this lemma tells you that can be proven like by direct computation. There is no like tricky argument behind. Okay. And actually, like not only it's like monotone, but also like you can estimate, you can have like an expression for the difference for the difference of the rescaled energies at two different radii. But let me not write it. So this is the first claim. I mean, the first important result is the monotonicity of the rescaled energy. Then you prove like the following epsilon regularity. So this type of statement is a very general statement in for systems or in regularity in general, is that you prove the following, like there exists a constant, epsilon not positive. There exists also a small constant close to zero, such that if U is from B1 into N is minimizing, and the energy of U in a ball of radius B1 is less than epsilon square, then you have the following decay of averages. So you have a small constant in front of and a small radius, such that so it tells you that like this is the so-called epsilon. So this is a epsilon regularity. So by this you mean like, so this is like the canonical example of an epsilon regularity. It means that assume a quantity is small in a ball of radius r, then so this is a type of statement, then like you have like a regularity holds in a ball of radius 1 over r, r over 2, in a smaller ball. So like so the whole point in this type of statement is what, like finding which type of quantity has to be small so that like in a smaller ball you do have regularity. Here this is the energy. The control of the energy small enough gives you like why the conclusion of the lemma is regularity. This is because it tells you that averages, like rescaled averages of the gradient, are like decaying geometrically. Okay, like because theta naught is like a constant small to small compared to 1/2, and here you have 1/2. So it tells you that like some averages of the gradient are like decaying geometrically, like as soon as in a bigger ball, the energy is bounded. And if you use like Moray type estimates, so like some characterization of C alpha, the fact that averages of the gradient square like are decaying like geometrically, it implies that the solution is C alpha. So the conclusion of the lemma is giving you continuity under like an a priori bound on the energy. Are there any questions or so this is really like the most important somehow lemma to prove, because it like triggers all the partial irregularity. This is really like the main lemma. Okay. So there are several ways to prove it. In the case of minimizers, one do not need to use the theory that, I mean, the arguments that I described last time. In the case of minimizers, you still use some kind of like structure of the right-hand side, but in a much less like sophisticated fashion than the argument last time. So because for minimizers, you can use competitors, and you have energy bounds which are coming from competitors. You have more tools than just the equation. Okay, so this lemma, even if it's not at all like an easy lemma, like does not require as much technology as what like I described last time, whenever you consider only like a weak solution. So this is like once you have proved that, like you are in good shape to prove the following last lemma, which is basically like the last basic lemma, okay, which is somehow telling you how to describe the singular set. So the sets that I called sigma before. Not only this is like the place where the map is not continuous, but you have more. You can prove that the density, this is a place where the density is too large. And what is the density? The density is the limit when r is going to 0 from above of r to the 2 minus n, the integral of br of x, like gradient u squared. So you see, like here, this is like a rescale energy, except that you take the limit. And why this limit exists? This limit exists because this quantity is monotone, so it has a limit from the right, from above. And this limit is called like the density of u at the point x. And what is the lemma 3 telling you is that you are in good shape to start investigating the regularity, because you can prove that the singular set of the map is not only the place where u is discontinuous, it's also the place where the density is too big. Because if the density is small, then the epsilon regularity applies, and you have regularity, Hölder continuity. So like this lemma tells you that not only the set is that, but a standard covering argument will tell you as well that the Hn minus 2 Hausdorff measure, and this is just a covering, is 0. Okay. So these three lemmas are not enough to give you the statement that I gave you, because like the statement tells like that not only like the set sigma is closed, but on top of it you have a Hausdorff bound on sigma, like which is much better than what I stated here, like the Hausdorff measure n minus 2 is 0. So you need to do more, but actually, like these three lemmas are like the main core, like of their partial regularity statement. Okay. Are there any questions or like? I didn't give any proof, of course, and so on, but at least I try to explain what is the strategy when you reach this type of problem to address the partial irregularity. Okay. All right. So actually, like now I would like to if there is no question, like so basic, I kind of tried to give like an insight of on what's going on, like for classical maps. And what I would like now to address is the case of like the free boundary case. So basically what I would like to address, so let me so is it visible? Everybody, like no problem?
Yes. So that's
Okay.
so in the previous case, you proved that Hn minus 2 of sigma equal to 0.
Yeah.
Then how do you get Hn minus 3 measure would be finite?
Because like you have to use several things. Like first is that limits of minimizers are minimizers. And then you have to use like a geometric measure theory argument of Federer to be able to understand what are like the elements which are contributing to the singularity. So it's not only a covering argument like dimension reduction. So it requires more tools from GMT, but somehow like what I just like stated are the main the basic points to have to start like this type of statement, and then after that to have like bounds like as I stated like hn minus 3 bounds, I mean codimension 3 bounds. Then you need to use more like properties of minimizers, and also like actually some kind of abstract arguments about densities. So it's like, but at least like what I explained, like it's something which works also for stationary. But these are the first step. Like as I mentioned, like you have to do more, like to be able to prove the statement I wrote. Is it clear?
Yes, thank you.
Okay, so what I would like to describe now are like a really a topic which is also old, but in some sense like goes back to and for which there have been a recent revival uh, 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 because of important result in geometric measure theory, like and geometric analysis that been investigate. So let me. So what I would like to discuss are harmonic maps with free boundary. So let me explain you. Let me come back first, like to the classical case of mapping. So what we like to explain first, I would like just to give like a reminder of one of the possible motivations, or several of the possible motivations of looking at harmonic mappings. One of them is one motivation is understanding the homotopy classes of maps between two manifolds. So this is something related to topology. You want to understand like how we can deform continuously like maps from between two closed manifold, and the question is that you plan to answer what are the is there like given an homotopy class, is there like an harmonic representative? Okay, so this is like what Ilse and Sampson in their original paper tried to address. Okay, is it clear? Then another one is like as I was mentioning, trying to prove some vanishing theorem and some Liouville using Bochner formulas, right? This is you try to kind of prove that the fact that like you have some Liouville, so typically no harmonic map, no non-constant harmonic map always gives you like some kind of geometry or topology information on the manifold. And we were always considering like M with no boundary. And in dimension one, this is for the domain, this is like geodesics, parametrization of geodesics. And in higher dimension, you can think that it would be like minimal submanifolds. At least a parametrization of it. Right? So what about M which has a boundary? Well, for sure, like what you can do, like for sure, is putting a Dirichlet data, right? So trying to solve something that we did like before, like the minimizing problem. Like you fix a boundary data and you want to like construct like an harmonic map in the inside. Okay, but this is not what I want to do. What I want to address is the following: somehow leaving the boundary of the domain kind of free, in the sense that just like putting a constraint, but not putting a Dirichlet data. So you see, like you have two manifold M and N like before, but now M has a boundary, and you take a sigma to be like a submanifold of the target without boundary, and you say that a continuous map which is on top of it, between M and N, satisfying the constraint that the boundary of, it maps the boundary of M into this like new manifold sigma, it always defines like a homotopy class in a reasonable sense for maps with boundary, which is called a relative homotopy. Is it clear? But you see, like I'm not fixing anything on M. I'm just putting the constraint to stay like in a submanifold of the target. So basically, once you introduce this the problem in relative homotopy, you might think that do I have like an harmonic representative in this setting? But what is like an harmonic map in this setting? Because of course, like now I have a boundary condition and I don't have a Dirichlet, I have a boundary, sorry, and I don't have a boundary condition in the Dirichlet sense. I have this like constraint. And so this is like the system that you get when you do the first like variation of such mappings. You get like an harmonic map, but like on the boundary of the domain, you get this geometric Neumann condition. So it's exactly like it's a geometric analog, if you want, or like a nonlinear analog of taking like a critical point of the Dirichlet energy without prescribing the boundary data. Then what you get is like Neumann condition, and this is exactly what happens here. Except that here somehow you have two constraints. Like the first constraint that U is mapped into N, but also like you are forcing U to map the boundary of the domain into this new submanifold sigma, which could be like, which is not all of them somehow, which is at least like a hypersurface. Okay, so these maps are called harmonic map with free boundary, which is quite a bad name because this is not a free boundary in the PDE sense. This is not that I'm trying to solve a problem like where I don't know the domain. Like it's really like just you are leaving you are not putting any boundary data on your domain. So somehow like you are leaving the boundary free. It's, I think, the reason why they call it free boundary. Are there any questions? No? So somehow, like this condition, this problem with boundary is a very natural one, like much more natural than actually the Dirichlet problem. Geometrically, it makes much more sense to look at this type of problem than fixing boundary data on the domain, on the boundary of the domain. So what I would like to explain now is that. Okay, so this kind of new system of harmonic maps where you recognize inside, I mean, in the domain, like the equation that we know of harmonic maps, but where you have these boundary conditions, very nonlinear boundary condition. Okay, so it's been studied at least like for a long time by the German school, and recently it's been reintroduced or at least like reactivated because of important results on some spectral problems developed by Fraser and Shane. But it's an old problem. Like there are old papers already looking at this problem. So it's not something new somehow. But there have been just like some sort of revival recently. And I would like to describe a little bit one of the reasons why there have been such revival. Excuse me. Is there any question So this is like a very this is really like a system which is very similar to the one we looked at, except that now there is a boundary condition which is also something like of harmonic map type, like a really like a very non-linear boundary condition with some structure, because like I look at this orthogonality with respect to the tangent plane. So it's really like a system like mixing where you are nonlinear inside and nonlinear on the boundary. And the thing is that of course if you have in mind if you keep in mind like what I described in the last lectures, inside we know already a lot of things, at least like regularity and but many other things. And so basically like the whole study of this system boils down to understand better like the boundary behavior, given like you have this boundary condition. Is it clear? So it's been studied by a lot of people, again, there are like many but what I would like to do is to describe a new viewpoint which is related to some maps which have been introduced much more recently, and which offers like a kind of a new light on this system, and which allows to some extent, that I will explain in the next lectures, to prove new things, because of reformulations that we talk about now. So let's take let's look at a very special solution. Let's take the following. Let's take n. So my manifold to be like a flat torus, like something which is compact but like flat, is just like a trick, just to have like the following system. So your map U starts like from the half plane into like a flat torus. Okay, so Laplace U will be 0. There is no the second fundamental form will be vanishing because you are Euclidean. And let's take sigma to be S1, the circle. Okay, then you get that this system becomes this very simple system. Sorry. Everybody agrees with that, or right? Okay. So once again, I'm keeping in mind that all the things that I want to understand and is a boundary behavior, at least how the boundary plays a role for the system. So the first claim that I would like to make is that if you have an harmonic function and you look at what is the derivative on the hyperplane, so the Neumann derivative, I would like to claim that this is the power 1/2 of the Neumann of the Dirichlet trace. So to prove that, this first claim, I mean, maybe it's not clear, but you have an harmonic function, it has nothing to do. So first, sorry, there is a typo here, it shouldn't be 0t, it's a stationary equation. So you have a harmonic. The first claim is not related to the system. The first claim is a general fact when you have an harmonic function, which has some decay at infinity, then the Dirichlet to Neumann map is the power 1/2 of the Laplacian, but in the variables of the boundary. This is what the claim 1 is saying. Okay. So this can be checked formally, but you can give it the sense also. This can be checked formally by just looking at Fourier transform in the unbounded variable and then solving the ODE. And you see, like, because the Fourier transform of this operator, like square root of the Laplacian, is modulus psi. I mean, it's a multiplier of symbol mod psi. But like if you use this fact that then like the boundary condition, so this is a claim too, the boundary condition write down just that the fact that the half Laplacian of V now is like the trace on the boundary. So it's only like a function of one variable. The half Laplacian of V is orthogonal to the tangent space, tangent line at V of S1. This is reinterpreting the third equation here. The thing is that what is like root V? Root V is you can define it like by means of a kernel, and if you write what this condition means, this is exactly equivalent to this equation that I wrote here. So maybe maybe like is there any question like
So if you replace the S1 by S2 or some Sn, then the last conclusion would be the same.
you mean like replacing H1 half with another one?
The target constant S1, the circle by sphere.
Oh, no, yeah, like if you replace it by any sphere, like yes, like the conclusion will be the same. Because it doesn't depend much like on the dimension of the target here. It depends how you define somehow like the square root of the Laplacian, which is I'm gonna describe now. But like if you are somehow like away from S1, you are like in any sphere, like you're gonna have like an equation which looks like this as well. But this equation is an harmonic map type equation, right? Because imagine that you define your like H1 half norm by the double integral, like Gagliardo. Then like you see like this term here is only like one integral. So this means that this is L1. So this is really like some sort of harmonic map equation whenever you replace the Dirichlet energy by H1 half energy, like so an energy associated to H1 half semi-norms. And this is really what happens. This is really what happens. So somehow like this problem is equivalent like writing everything on the boundary. This problem for you like is equivalent to looking at the trace like and the trace satisfying this equation. But the thing that you see, like it gives you a dictionary somehow, because if I have a solution of this equation and I extend it harmonically in the half space, then I have exactly the solution of my system. This is like exactly my construction. And vice versa, if I have a solution of my system, if I take a trace of the boundary, then I have like I have a solution. I have an like a function satisfying this equation. Okay. So somehow, like I have like reduced the whole problem like to an equation on the boundary, except that the equation on the boundary pretty involved. It's like non-local, non-linear, of course, but at least like somehow I have like reduced my problem. Are there any question? Like, does it make sense? So now, like somehow, like I can choose whatever representation I want, like at least for the class of harmonic map with free boundary when n, like the target, somehow, the general target, I should say, and like is a flat, I have this representation. Of course, originally I didn't have like a flat, in general, my system here has a right-hand side, right? So n, like the target n is not necessarily flat. but at least like as far as like the regularity is concerned somehow at the boundary, like I can reduce in this case to this equation because, and this is something somehow which matters because like, you know, if I'm harmonic, like, or if I have even like an harmonic map system inside or in the interior, like I know how to deal with it, like I'm away from the boundary. Okay. Are there any questions or no? So this somehow this phenomenon is a kind of reminiscent like of the famous like Caffarelli Silvestre extension. So which amounts somehow to understand like any power on the boundary in terms of a suitable extension inside, which is not necessarily like harmonic anymore. So I will come back to that like in a bit, but like here, like I just consider it was just a case s equal to 1/2 because it's like I'm considering an harmonic function. Is it clear? Is there any question or like? Okay, so now I should describe, well, okay, what did I gain? Like, what did I win? Like, by looking at this equation in this formulation somehow, right? Because after all, like, this formulation is quite involved, even if, like, the function now depends only on one variable because it's on the boundary, it's still like you might ask, like, why is it that better? Or at least, like, why is it useful, I should say, right? Excuse me. And so let me explain you like why like I mean like possible like how can I say like a possible explanation for that. But first, like let me are there any questions or everything is clear or do you want me to explain something a little bit more with details? So a few years ago, like Dalio and Rivière introduced like the concept of like half harmonic maps. So like they look exactly what I was looking at. Like they look at an energy, which is this E1/2 energy for map U, which is from the real line into any target. Okay, like you can think about the sphere. And they prove like the Euler-Lagrange equation like of these maps are exactly the maps as I define them here. Okay, so somehow like this like a particular class of harmonic map with free boundary happen to be like just a variation of this half harmonic map that Dalio and Rivière introduced. Cool. And this is like somehow like where like some these things are start being useful because somehow like like they develop tools which are like intrinsic to this non-local equation, or in other words, like really like expressing the globality of the problem. And recently, in the last 20 years, because of this Caffarelli-Silvestri extension in particular, there have been like some sort of extremely like developed regularity theory and like many other tools developed like for like exactly these non-local equations. So somehow one can hope the following, like using these tools for non-local equation to be able to answer like some problems in the case of harmonic map with free boundary, like in the classical formulation. And this is like what I want to advocate. And the reason why, one can understand all these tools, or at least like one can use all these tools, is because like there is this formulation in terms of these non-local equations. Okay. But of course, as I was mentioning, like the case of harmonic map with free boundary has been studied way before. So somehow the regularity of this half harmonic map a la Dalio and Rivière, at least for some cases, like it's kind of like reinterpreting like a result which were known for harmonic map with free boundary and just taking the trace. So somehow like this is what this statement like is saying, that those maps, so really like are half harmonic maps in the sense of Dalio and Rivière, which are just traces of harmonic extensions, okay? Like traces of these harmonic maps with free boundary. They enjoy some regularity, which is just like known from like the free boundary case. There are other things which are not known in the free boundary case, but as far as the regularity is concerned, at least like there is like a like uh, quite decent theory, and what you can see is that here, like full regularity does not happen in 2 dimensions, but in 1 dimension. Maps from the real line into N are regular. This statement here, used to in the case of standard harmonic map, it used to be in dimension 2, that there was no singular set. In dimension 2 and higher, if you are minimizing, then like you recover like the statement that I gave before, that you are discrete in dimension 2 for the singular set, otherwise you have codimension 2 bound. So like everything for those maps, these half harmonic maps, everything happens like in one less dimension. Has any questions or? So somehow using this analogy, one could like actually kind of push forward the study of this harmonic map with free boundary, because they happen to be just like special like variations whenever of some other maps, whenever you write everything on the boundary. And this is exactly what this theorem is saying. So now you can ask like other examples, and let me give you one example of such half harmonic map. If you take this map here, 2x over x squared plus 1 and x squared minus 1 over x squared plus 1 from the real line to S1, this is actually satisfying this equation. And so there are examples of such map, and of course, like any rotation and translation and dilation, are also satisfying the same equation. So there are examples of such map, and this one is a half harmonic map. But if I take its harmonic extension, like to the half plane, then it becomes a solution, a weak solution of this equation. So it becomes an harmonic map with free boundary in this sense. So are there any questions or?
Hello, sir. So about the Schoen-Uhlenbeck theorem, like how the sharpness of the, do we have like sharpness of the per bound on the Hausdorff dimension there?
Yeah, like you can prove in dimension 3 that actually even in dimension 3, x over mod x is a candidate for discontinuity. So like x over mod x is a minimizing map.
Yeah, I mean, like given any subset with that prescribed Hausdorff dimension, whether you can construct a harmonic map with that prescribed singular set.
Okay. This I'm not sure. I'm not like my guess would be yes, because like it's probably a construction. It's already in some papers of Bresis, Coron, Lieb, but however, like I'm not sure if it's more formulated this way, if you can kind of like prescribe the singular set.
Okay.
I mean, like really like kind of gluing somehow, like some of these singular harmonic maps. I'm not sure, like one can do that. I would guess yes, but I would need to check. Yeah.
Okay, and so if you have some time in the next few lectures, if you kindly give a bit more details on the arguments of Schoen-Uhlenbeck, that would be very helpful.
You want to have more details on Shane-Uhlenbeck? Okay. I can give
Great.
more details next time. This is not like both like the proofs are not easy. Yeah, but all the proofs are like kind of, and particularly of the epsilon regularity. But if you want like to have more details on that, like I can, yeah, for sure I can do that.
Thank you, sir.
I can explain like how to prove the decay.
So any more question? So I have one question regarding how you posed the free boundary problem. So you have a condition on the boundary value of the function as well as its derivative. So is it an overdetermined problem?
No. This is not a condition. Okay, that's a good question. This is not a condition on the. This is a constraint. This is not like I'm not fixing the boundary value the boundary value per se. Like this is really like a constraint. So it's not an overdetermined problem.
Okay. So
Not overdetermined.
and one more question: the way you formulated the energy functional and the minimization. So in that, I think it's in the second slide. So in that case, your so in this one, you have the constraint maps only with the boundary lying in sigma. So
Yeah.
Will it imply that your normal derivative is perpendicular to the tangent space?
Yeah. This condition, this constraint, like when you do like a first variation, this constraint like lifts. I mean, it's expressed through this Neumann condition.
Okay.
When you write down like the when you write down the Lagrange equation, so you do first variation and exterior variation. This is exactly what shows up.
Okay. So we cannot actually prescribe, like, can we have solution when the normal derivative is belongs to the tangent space, like for this?
No, then this is not, no, because like then this is not the same problem. This is not the same problem, because like it's really this constraint which kind of like gives you like orthogonality. in
Yes, so
exactly the same way, like the constraint of being in the target N was giving you like this like orthogonality in the interior.
okay. Okay, so let me be clear. So will we have solution if the normal derivative lies in the tangent space, like not via this constant
No, like
minimization?
what, yeah, like I don't know what you would need to put for the derivative living in the tangent space. Yeah, you might have solution of some. Yeah, but like you mean living in the tangent space, or orthogonal to the tangent space? Because my system, like you have to be orthogonal to the tangent space, and yes, there are solutions, right? Like this is oh, let me. There are solutions. Like if I'm orthogonal to the tangent space, the solution I described, like at the end of my slides, were like are solutions of this equation. But you are talking about a different system, like when du
Yes,
nu
yes,
is like a lying, so it's
yes.
another type of thing. This I don't know.
Okay, okay. Thank you. That's all.
So any more questions from? So from the, if there is a question from online participants, please unmute yourself and ask.
Yeah. Hello.
Yeah.
Yeah. So it is a nice talk. I just had a question because here, A of you, are there, is this problem studied for certain special cases of AU? Like, can you?
Yeah. Like as before, like there have been like some studies whenever like the target is like negatively curved, for instance, or like so this is a classical harmonic map equation because I'm
Okay.
considering maps from M into N.
Yeah. Yeah.
So yeah, like it's been studied in some special situation by even going back to Hamilton in the 80s or like or the 70s, sorry, or something like that.
Okay. Okay.
But it's not like I mean like because now there are three spaces, right? There is M, N, and sigma, and so one or three like ambient spaces. So
Yeah.
somehow there is an interplay, and it's not completely obvious, like to how they interplay with each other. Like so, for some like targets N, like as a general space, then there have been some results. Like, but yeah, not all the cases have been like investigated.
Yeah. But in that case, in those special cases, do you still get that half Laplacian type of equation, like
Yeah.
the equivalence which you showed about the extension?
Yeah. Like this equivalent
Yeah,
holds all
yeah,
the
yeah.
time, even like not only for the sphere. Like what we might not get, like is such a like a nice equation, but however, this equivalence that I described here, like somehow, like the first two claims, yes.
Yes, okay.
And actually, like somehow Dalio and Rivière and Chicora afterwards have been like working out like what would be like an equation which is useful to like interpreting this condition, the orthogonality condition, whenever you have like a general target.
Yes.
But
And
like it's yeah.
no, and as one of the participant already asked, so instead of S1, if we replace
Yeah.
with higher dimension, the
Yeah.
equation, this equation, the half Laplacian equation, does it imply anything geometrically or?
Yes. Actually, this is, I mean, geometrically, it's just like a reformulation of this problem.
Even for higher dimension? If you replace S1 by Sn, that's what.
Yeah, even in higher dimension. Yeah, you are just like considering other types of harmonic map with free boundaries.
Okay.
Like you are just like considering other types. So yeah, like geometrically somehow this is like this half harmonic equation is useful analytically because you can use but also like up to taking an harmonic extension, you can. These are classes of harmonic maps with free boundary.
Okay. Yeah.
That's a good question.
Thank you.
So here you use the target as codimension 1, right?
Not necessarily
Not-
here, like in this example, yes, but you like this condition holds like for
No,
any like
for the last conclusion.
yes, yeah.
And you mentioned that the inverse of the stereographic projection is a solution to this last PDE.
Yeah, when
So
the target
is there easy way to see it, or because computing half Laplacian
there
is
is
not
no, like, it's a direct computation, but it's not exactly a direct computation. Like there is no easy way, at least like that I know of, to see it. Like because somehow like the computation that you want to do with these equations are very nasty because you have all these like global terms coming from the integrals. So I have like no easy way to prove that this like stereographic projection somehow is like or the inverse of the stereographic is like a solution of my equation somehow. It's always using like an indirect like argument.
okay. So are there any more question? Looks no. So yes, thanks
So
the
what I
speaker
will
again.
do like next time indeed is like explain a little bit more on the proof of Shane-Ulenbeck if some yeah if to give more detail on how to deal with like epsilon regularity in particular.
Okay, thank you.
Okay.